So welcome back. So the first speaker in the afternoon session is Constanze Roitzheim, and she'll be speaking on continuing her talks on chromatic homotopy. Thank you.
Thank you very much. Thank you for coming back from all the lunches and coffees and naps. It's very nice to say that I'm continuing to do chromatic homotopy theory, because I think last time we more or less got to some of the setup. So let's remind ourselves again of the goal. So the goal was to study the stable homotopy category which I continue to consider to be the homotopy category of sequential spectra, even though there are, of course, lots of other forms of spectra are available. And the message was that this was very big and very complicated because it contained a lot of stuff. So, for example, I said it would contain a kind of non-stable topology that people know. So if you take A to be a pointed topological space, then you can form, you can make that into a spectrum by taking the suspension spectrum. I'm also doing that to just get a little free reminder of what sequential spectra look like. So a sequential spectrum was a sequence of pointed topological spaces with a structure map from the suspension of the ith spot to the next spot. And in this case, it's quite clear what the structure map would be. So that is a way, for example, to consider all of classical topology to be included in here. But the kind of blanket, arrogant statement that homotopy theorists make is, of course, well, it also contains all of algebra. And when algebraists say, well, does it contain that? We'll say, well, that's not very interesting because it's not in here. So it's kind of a bit of a self-made statement. But let's make that a bit more precise by what I really mean and introduce some more notation at the same time. So if you take G to be an abelian group, then we know Allenbach-MacLane spaces. So always make sure to leave a gap. Make some referees very angry if you don't leave the gap. No hyphen, Allenbach-MacLane space. Like the nth Allenbach-MacLane space would be a space characterized by the following: space with one unique homotopy group, G in degree I and 0 elsewhere. So that is how to take a group and make it into a space, but you could also make that into a spectrum by, well, it's denoted Hg rather than Kg. So you can form a spectrum by taking all the Allenbach-MacLane spaces of G, and the structure map would be adjoint to the equivalence that identifies Kgn with the loop space of Kgn plus 1. So let me just write it down because it's easier to believe me when you can see it, hopefully. Because if you write down the homotopy groups of this thing with the usual loop suspension adjunction, that is also going to be a Kgn, and then you get an adjoint map from sigma of Kgn to Kgn plus 1, and that would be the structure maps in the spectrum. And if you write down what the homotopy groups of that spectrum would be with the co-limit construction that I showed you last time, you would always just get, well, in the correct degree, well, in degree I equals 0, you would just get G, 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 G in your co-limit, and you would get 0 in all the other degrees. So that would be exactly, well, not quite the same thing, but I'm already running out of space. What is that like? So phi naught of Hg would be G and 0 elsewhere. And then, of course, by suspending it in whatever direction you want, you can also get an Eilenberg-MacLane spectrum for other degrees. So we are really only going to see HQ, I think, today. But yeah, that is a way to consider all abelian groups as part of the stable homotopic category. Well, that, of course, is not that much algebra yet, but there are more structured Eilenberg-MacLane functors. If you're into that sort of thing, you can define, well, it's very easy to look at generalized Eilenberg-MacLane spectra, which are associated with graded abelian groups, but then you can move on to chain complexes, DGAs, and other Eilenberg-MacLane functors that takes the more highly structured algebraic objects and also make a spectrum out of it and therefore consider it as a part of something living in a stable homotopic category. Something else that I will say quite a lot is maybe a little more sophisticated, because there is the Brown representability theorem, which tells you that not only do the objects in here define cohomology theories, but also every cohomology theory has a representing spectrum. So what do I mean by that? So if you have a spectrum E, then and now I never know if it is a plus or minus. The following thing is a minus. I wrote both in my book. One of them is wrong. So that would be a cohomology theory in the sense that it satisfies the Eilenberg-Steenrod axioms. And that is not that hard to check. But the converse is also true. For every cohomology theory, there is also a spectrum. So if you have a favorite cohomology theory, maybe K-theory, singular cohomology theory, or other things, then there will be a spectrum representing it. And just because that's what I'm used to in the way that I talk about things, I use the two terms interchangeably. And mostly I will actually be talking about homology theories. So for a spectrum E, the corresponding homology theory is going to be defined as so. So if you take all of these three things, and you see that this contains topology, it contains algebra, and it contains all cohomology theories, then you can hopefully believe that this contains one hell of a lot of mathematics. And therefore, it is big, it is complicated. And one would like to, well, whenever anything is big and complicated, what people like to do is break it up into more manageable pieces. So you need to understand the smaller pieces, but also how these pieces work together in order to recover the big picture again. And that is really what chromatic homotopy theory is about. So the first question is usually, like, why is it called that? Because what I just said about breaking something up into smaller pieces and reassembling it, that's not exactly niche. So I always wanted to talk with background music. But as I said, from my experience with Shah Rukh Khan movies, I was hoping for something a bit more rousing. This particular decomposition that we will work towards is almost like decomposing the stable homotopy category into different layers. So I will not draw this because it's just a bad picture and it is also outdated and out of fashion. So first of all, just as in algebra, you can chop up your integral information by localizing at primes p. That is nothing particularly new. So let's just say, so for each prime p, you get a block of stable homotopy category, but each of these things is just as terrible as the original. So you don't really gain anything by just p localizing it. It is nicer for writing down certain things. It is nicer for certain calculations when you can just look at, let's say, p stems of homotopy groups rather than all of them. But first of all, you decompose the stable homotopy category into p local pieces. And then you can think of each p local piece as a skyscraper with infinitely many floors and layers. So you kind of get layers. And these layers are considered to be the chromatic layers. And this name chromatic comes from just school chemistry, where people try to understand a chemical by dipping a paper into it and seeing it rise up and make lots of nice stripes of colors. And then from these colors, you can say, oh, maybe that's that. I don't know, it's a long time ago. And in chromatic homotopy theory, people try and do the same. There are certain things, and people would like to see which layers does this live in, how does that interact with other layers, and what does all of that mean? So this idea of decomposing stuff into layers that's kind of come on top of each other, I guess that's where the word chromatic really comes from. But we still have quite a long way to go, because decomposing things is, well, it's quite a non-trivial tool, even if we want to say we want to just p-localize, because what does that even mean? So in here, the pi star isomorphisms, well, became the isomorphisms in here. So in here, two things are considered equivalent, isomorphic, if they are related by homotopy groups. But there is no reason why you necessarily need to stick with that. You could maybe take that instead and consider things to be the same or equivalent if they are the same through the eyes of your favorite homology theory, not just through the eyes of homotopy groups, but maybe you would like to live in a world where you consider things to be the same if they are rationally isomorphic. Yes, John is awake again. Maybe you would like to live in a world where things are the same if K-theory thinks they are the same. And this is something that one can make formal via left Bowles field localization. And that is what we will talk about next. We have seen a lot of right localization in Shrikant's talks, which is generally considered to be harder. So you're lucky, this is much easier. So this is how this works in general. So let's look at the machinery for inverting more morphisms. Not just those, but I would like to have some more. So let's say I take a class of maps in here. Then I would like to add these to my isomorphisms in here. And we know that if we just say, oh, I now declare these to be isomorphisms, and then I let that generate me some new category, that is set theoretically very dubious. One has to be very careful. And if you are a homotopy theorist, you would do the things that I would tell you now. So first of all, we need to define the following, namely that a spectrum is W local if it can see the elements of W. So what does that mean? So if for all maps in W, the induced map, where I will put the X in the second spot, this is an isomorphism. So W local means this guy sees the maps in W. And once we have that, we can say that a map G from C to D is a W equivalence if it can see the local objects. So if for all W local X, you get an isomorphism out of it again. Okay, so you can see you start with a class of maps. From that class of maps, you define yourself some objects. And from these objects, you define yourself more maps. So it is to note that W lies inside the W equivalences, because by definition, you can just see that. But in most cases, you make more. Well, you don't really know just from looking at that, but believe me, in most cases, you start with something and then you make some more maps. And of course, you could say, oh, let's just continue for the fun of this and replace W with that and run that through the definition again and see, maybe you can look at W equivalences and get even more maps. But no, actually, this process stops here. So that's something mental at least. So this actually it stops there. This process stabilizes. Did I write it down correctly? No, I didn't. Thank you. So there you can see that in this random definition here, this process already seems to be closing W under something reasonable. And maybe I should just say, just because the word is going to be mentioned in a bit, you say that X is W acyclic. Let me just squeeze that there. If X is a bad name, it's exactly the other thing that you would put in the exact triangle. So W acyclic is all the things that the locals consider to be invisible, just because I might mention that and then I haven't really said what that is. And another thing to notice is that also just by definition, by looking at it, you can see that those W equivalences also include pi star isomorphisms. So we see that here we have something relatively reasonable that includes these things and this, whatever that W is. So what we would therefore like is this one to be a new choice of weak equivalences for a model structure on spectra, which would then give me a homotopy category in which all these things are still isomorphisms, and these things are still will become isomorphisms as well, and hopefully that would be reasonably closed under the things that it would automatically have to be closed under. So here, this has a name. So the W local model structure on spectra is the following. The weak equivalences are the W equivalences. The cofibrations of this are the cofibrations of the old model structure. And the fibrations, well, are what they have to be. So that is really just a cheap cop-out, you might say, saying, well, it is what it is. But in fact, something I probably should have mentioned yesterday, in the definition of model structures, one of these two is always redundant information. The lifting axiom that I didn't write down, maybe you saw it in your prep talk, I don't know, forces one from the other. So in theory, you define a model structure completely by just writing down these ones and these ones, or these ones and these ones. In practice, that might not be particularly helpful because sometimes you can just say what these things are. Sometimes you need to know what these things are, but sometimes that's really all you can say. But so in order to define this, you change the weak equivalences, you keep the cofibrations to be the same, and then the fibrations will automatically change in a mysterious way. This also has a name. I should really have given it a name. And there it is. And now, hopefully, anyone who's ever seen a model category before will feel very, very uncomfortable, not because this is wrong, it's perfectly right, but there is not necessarily a reason for this to exist. Whether or not this exists very heavily depends on what that W actually is. So a lot of theorems and lemmas and whatever of that kind will say, if it exists, that's what it is. But it is not clear at all if you write this down and say, that this really works. So the most used reference for the existence of such a thing is Hirschhorn's book, but others exist. So if your W is a set rather than a class, then you're good. So that is nice, but I said we wanted to invert E star isomorphisms. That's not a set. So you have to do extra work to show that you can do that for E star isomorphisms. And well, I would guess my go-to reference for that would be EKMM. Others are available. For E star isomorphisms, there is work to be done to find a set most commonly denoted by J lower E, such that the JE equivalences are exactly the E star isomorphisms. So that is all good. So all the set theory has been done by people to make sure that we are also allowed to say what the E-local model structure on spectra would be, and therefore allowing us to form the E-local, or here in this case more generally, the W-local stable homotopy category. Yes, the factorization is the one. If your model category is stable, one can simplify the existing proofs, but I still find them hard. So let us now assume that the work has been done and it exists and we are allowed to talk about it. Then let's look at some properties. So first of all, we can just continue look at the identity functor, because, well, this and this, that's the same category. It has different model structures on it, but it is the same category, so we can just apply the identity functor. But it has different model structures on it. So it isn't necessarily compatible with the homotopy that arises from it. But in this case, of course, we are in luck, and the identity forms a Quillen adjunction. So in particular, if you don't remember the definition, it induces an adjunction between the stable homotopy category and the W local stable homotopy category. And if we zoom in away from the whole category back to just individual objects, the new fibrant replacement in that model structure gives us the following. So fibrant replacement, we talked about last time, is where we take an object and replace it with an equivalent object that is nice in this case, it means we take an X, and the fibrant objects in here are precisely the local objects. And that is a W equivalence, and that is a W local object. So the model structure gives us, now once one knows it exists, a very simple tool to take an object, replace it with a local one, and the W, or in our case, the homology theory, will not see the difference between them. For those of you who like universal properties, that is more or less rewriting the definition here, but it's nice. So if you take a map from any X into something that is local, then of course you have this localization map here as well. And then there is a unique map from here to here. So any map into something local will factor over the localization of the first guy. So we arrive at a very, very nice triangulated category where things are considered to be the same if your homology theory thinks they're the same. If your homology theory thinks that something is trivial, it actually is trivial in there. If your homology theory thinks two things look the same, they are actually isomorphic in there. So that is a very good tool to have. Right. So let's start with some homology theories. Let me therefore localize at the following. So for every abelian group G, one can form the so-called Moore spectrum, which is kind of the cousin of the Eilenberg-MacLane spectrum. So it does for what the Eilenberg-MacLane spectra do for homotopy groups, Moore spectra do for homology groups. So a Moore spectrum is a spectrum that has a homology group G in degree 0 and 0 elsewhere. So the sphere is the Z Moore spectrum, which kind of indicates that so those guys are the ones with easy homology and horrific homotopy. And the Eilenberg-MacLane spectra are the ones with easy homotopy and horrible homology. So for example, the mod P Moore spectrum you could get as follows. You take the multiplication of by P on the sphere spectrum, and then the co-fiber of that would be the mod P Moore spectrum. I often just write it as M because I use it so often. For other abelian groups, you would just take a wedge of spheres for the generators of that group, another wedge of spheres for the relations of that group. And when you take the co-fiber of the map that gives you the relations, you quotient that out, and then you get a Moore spectrum for any group that you want. But just remember this as a toy example and this characterization, and you will be fine. So if we start, I want to start with localizing. What's the best cloth today? Not any cloth today. There's cloth. Yeah, there's a cloth. But the orange one was so nice. Is it cleaner? So first of all, I would like to start localizing with respect to rational homotopy theory, which would be the same as localizing with respect to rational homology. So what I didn't really say is that these guys are exactly the spectra that give you singular homology with coefficients in G. So if you want rational homology, so Q coefficients, you need to look at HQ, which is also, by a divine coincidence, the same as MQ, which normally never ever happens. So that's the only case that's meaningful where the Moore spectrum and the algebraic spectrum coincide. So let us localize with respect to some Moore spectra. So I would like to localize with respect to MQ, which happens to be the same as HQ. I would like to localize with respect to M of the P locals. And I would also like to localize with respect to mod P Moore spectrum. And these still sound like just very, very, yeah, not really worth the effort, because that's just, you know, some relatively simple algebra. But how these things behave is going to form the toy examples of how the higher chromatic layers will behave. So it's very well worth doing. So let's localize at HQ. So if we would like to know, okay, so what is Q localization? For all of these things, the main tool that really tells you all the things that I will write down in a bit, there is this universal coefficient short exact sequence that is, now there's indices involved. It relates homotopy groups really with these groups, and then and that's where the index shift comes in. So that is just the ingredient for the properties I will now start listing. Yeah, well, if I don't write it down, then that's what it is. So if we look at this map here, we can of course ask, so what is the localization map from here into here? Well, it is a map that's first of all supposed to be an HQ isomorphism, which means that it is a pi star isomorphism tensored with Q. And well, I mean, we know the homotopy groups, well, the stable homotopy groups of spheres. When you start tensoring them with Q, they all disappear apart from in degree 0, where they are Z. So whatever is left after tensoring with Q can only have homotopy groups Q in 1 degree, namely 0. So the Q localization of the sphere is just HQ itself. And in general, plugging that into the definition gives you that this is true for general objects. So the spectrum X is HQ local if and only if X is isomorphic or weakly equivalent to smashing it with HQ, which also, by what I just wrote, is smashing it with the Q local sphere. So really, on the algebraic side, rationalization is tensoring everything with Q. And on the topological side, when you Q localize, it is exactly the same thing. You just smash everything with HQ. And that is then, well, whatever that is as a space would be absolutely horrible, but the homotopy groups is what you will care about, and they will become very, very simple. And most of these things, well, you can extract that from the definition in combination with that universal coefficient short exact sequence. But if we do that for P local Moore spectrum, that works very, very nicely and in a very, very similar way. So the localization with respect to that, we call the P localization. And one can work out that this is precisely, so this localization map is exactly, again, smashing with the P local sphere, which you can find out by plugging it in there, knowing that, and this is also the P local sphere, and that these are the same thing. You extract that by knowing that this thing has P local homotopy groups, and then you can put them into some arithmetic square and very, very cleverly deduce that this one must be a P local isomorphism. So that is entirely arithmetic. So that all sounds very nice. And it also sounds quite easy. So is it really true that whenever we localize something, all we have to do is smash it with the local sphere? Wouldn't that be nice? And you can already tell from the way I asked that already when we're going to the kind of next harder case, the mod P Moore spectrum, this whole dream is already going to collapse. Henceforth, it is not as easy anymore as saying, oh, we're localizing just by doing the topological analog of just tensoring with that ring. That is not going to continue, sadly. So let me know when there's anything you can't read. Thankfully, unlike the more algebraic people, I don't really depend on indices as much. So hopefully it doesn't get too small. So because this is very nice, it deserves its own definition. We say that a localization is smashing which is also terrible English slang for great. If it is exactly of that form there, if, which letter did I use? Let's just concentrate on homology theories. If localizing is the same as smashing it with the E-local sphere, which is exactly what this is and what that is. And well, why are smashing localizations great? Well, first of all, it's very, very useful to know that they preserve compact objects. I mean, I now have, I'm in the great situation that after the talks by John and Henning and Rekha, I don't have to motivate why compactness is great and that's something you would like to see preserved under all kinds of things. Topologically, of course, the sphere is compact in the stable homotopy category, which means that you can build everything in the stable homotopy category using exact triangles and co-products. Therefore, you can build the entire stable homotopy category from cell objects from the sphere. When you localize, it's not clear that you still can. It has to be smashing for you to still be able to say, oh, in the E-local stable homotopy category, I can just build everything from the E-local sphere. And for that, you need this. And so, well, what I just said, in this case, the sphere is a compact generator of the E-local stable homotopy category. And well, smashing localizations preserve other things. Well, they commute with co-products. They have all kinds of nice properties that you would like, but don't necessarily always get. So if you have a smashing localization, consider yourself lucky, because right now we're going to fall into the absolute dark depth of despair of P completion. So if we continue, this one is not smashing. So how and why? Well, we just call the localization at this the P completion of X. Why would we call it that? So far, I've just defined something and not done anything. This is justified because if in each degree phi n of X is finally generated, then you can use that short exact sequence in a very unsophisticated and brutal way to show that the homotopy groups of the P completion are in fact the P completions of the homotopy groups. That is actually necessary. So that's just not always true. So if we look at the P-complete sphere, I mean, that's a completely horrifying thing. So the P-complete sphere, I will just write it down for you so that you will hopefully be convinced that you would never want to see it again as long as you live. It's that. It's some horrific mapping spectrum, and whatever it is, doesn't really matter, but the bottom line is that P completion is not smashing. So I personally find P localization very nice and P completion rather scary, but that is absolutely down to your personalities and preferences. Because, well, if you have certain people in the audience, they will say, but that is when it gets really interesting, and that is for just softies. It depends. To doing certain things, you need certain properties. And even though these things like P localization and P completion might look very similar computationally, just overall, they have very, very different properties. But yeah, if you are algebraically or very algebraically inclined, P localization and P completion may be exactly where you want to end your story, because you can recover all integral information from that. So there are various so-called arithmetic squares in homotopy theory, so often known by Bowles field squares. So you have certain pullback squares which tells you how you can reassemble all the information of a spectrum from these things there. So there's two, or the two most commonly used ones are as follows. You take rationalization. Did I actually introduce that notation? No, I didn't. Just call that XQ. And you know what I mean. So you can reassemble the information of X from the rational information together with all P complete pieces. And then here, well, you just get the rationalization of that. So if you know this and you know that, then you also know this. If you would like to read Bowles field's papers about this, good luck. They look very innocent on the surface, but whenever he mentions just a little lemma, it normally is 2 or 3 entire papers again. So these things are really to do a lot just with the naked arithmetic of the homotopy groups of these things and just how these things decompose as groups. But assembling it is quite hardcore, but thankfully people have done it, so we don't have to, and we can just go with it. Or, so here I've used rationalization and P completion. You can also use all of P localization, as in you can of course not just localize at 1 prime, you can localize at several primes simultaneously, which means just actually, you know, you localize them one after the other, which is the same as localizing simultaneously. You can localize at a set of primes, and then you take all the other primes and localize at them, and that reassembles into X. And of course, if you localize at all primes at the same time, that's the same as rationalization. So I'm not going to introduce the notation because I will never actually do it, but you can also reassemble spectra from just knowing all the P local pieces. So if you are an algebraist who's not at all topologically minded, then maybe the story really ends there, because you reassemble the integers from rational and p-local information, and that's it. You cannot decompose it any further. If you are a topologist, maybe that is the real test, whether you're an algebraist or a topologist. And this is the beginning of the story. You know, sometimes when you are a very algebraic topologist and other colleagues come to you and say, oh, but you're a topologist, can you answer me the following question? I've got this manifold, and then I always have to say, well, I'm not that kind of topologist, I'm sorry. Which made me think, am I even a topologist if all the mathematicians around me are always disappointed? But maybe that's the real test, whether you're a topologist or not, whether it ends there or it starts there. Because you can then, of course, take the stable homotopy category and decompose it. Well, you can write an actual error as part of that derived functor over there. And you get p-local pieces, and you can say, oh, that's very nice, because if you compute homotopy groups of spheres, you often just compute p-stems. The homotopy groups of spheres are complicated enough as they are, so it is much, much more manageable if you just look at the p-stems for one fixed prime p. And then what you really do is you calculate the homotopy groups of the p-local sphere. So that has arithmetic advantages, huge ones. But this thing is still just as big and complicated as that. So from the point of view of decomposing this into more manageable pieces, you haven't really gained much at all. But now this is where the topologists have the advantage over the algebraists, because where they have the integers, we have the sphere. And the sphere can do a lot more than the integers, which is really just hz. So now we have walked this way, and let's just say, I don't feel really tempted to use a different color just because they're there, and say, let's say from now on, everything I consider to do is p-local. That's quite silly because they all look the same from up there anyway. So let's take this and decompose it further, much, much further. So for a fixed prime p, I would like to define homology theories En and Kn and localize with respect to these and see what I get. And the reason I've done all this over there is not just to say how algebra is boring, which it isn't. The reason is that the Kns are going to very much behave like this, and the ENs are going to very much behave like those, but together they very much need each other. So now actually, we're not really going to go back all the way to the sphere. We're going to complex cobordism. So these imaginary colleagues will say, ha, you do manifolds after all. Sorry. What I really would like to sell to you is that as the representing spectrum whatever this may be, this is a very universal object. So for whatever your flavor and complexity and inclination within chromatic homotopy theory is, it usually always starts with mu or something to do with mu. Well, why is that? These things can get very complicated. I mean, I can just take a copy of Adams's book and just throw it in the audience and say, well, read it. The coefficient ring of it. I mean, just look at it. As a ring, that's a very, very nice ring, isn't it? And as a ring, this is already universal. It's a polynomial ring in infinitely many generators. So it maps into anything that you want. So just algebraically, it doesn't take much to believe that this is a very, very universal object, some free thing. But a lot of Quillen's work and Adams's blue book, which I would very, very highly recommend you read. Its disadvantage is the absence of an index, but I think now that somebody actually LaTeXed it, it has become searchable. It's beautifully written. It might be the only math book I ever actually read beginning to end. It will tell you that mu is actually universal among the topological side of things. So as I'm not really going to get into this, I will just say it. As a ring, this maps into a lot of other things uniquely because it's a polynomial ring on infinitely many generators. But mu is universal in the way that whatever this does on algebra, there is an underlying thing in topology which induces you the maps in algebra. So all of these topologically motivated things that you can do with this ring, you can actually do with a spectrum, and it will induce you the algebra. And that is a very, very strong statement and a very, very strong property. So in many regards, well, for chromatic homotopy theory, this is just as good and important as the sphere is. So it all really starts with mu. So let's just say universal. So even if you forget everything that I've just said, just remember it is universal. Everything you want to do in chromatic homotopy theory starts somewhere here. But I mean, I said from now on in pink, everything is P local. We might as well work with complex mu, but complex mu splits into lots of copies of shifts of a degree that I forgot. If anybody knows, let me know, of something called BP. And the coefficient ring of BP, we should try and remember, is almost the p-local version of this. So of course, as it splits into shifted copies of it, it is going to be more sparse than that. It's also a polynomial ring on infinitely many generators, and the generators are called Vn with degree 2p to the n minus 2. And from there on, I would like to, yeah, I've got some time, tell you what these things are going to be. And there you can kind of see a little bit, even though it's going to be quite hand wavy, what I meant by all the things you want to do algebraically, you can realize on the underlying topology. So the EN are called the Johnson-Wilson spectra. Because of course there is one, well, for each P and each N, you have one. And their coefficients, so they're homotopy groups. So that is just shorthand for these things. Is going to be, well, you start with the first n of these V's, and then for the last one, you also add the inverse. Looks random, but it's good. And then you have the Morava K-theories. These coefficient groups are a lot easier, but I mean, that is really the naughty one. That's the one that behaves like completion. This Laurent ring in that P. Yeah, and these ones you can construct from MU. So how so? Well, just think of exactly what you have to do to this ring to get those rings. And that is what we will do. But first of all, so for EN, you start with BP. And then what you're going to do, you kill some of the elements in its homotopy groups. So how do you kill an element in a homotopy group? Well, you apply the element of the homotopy group, and then you take the mapping cone, and then that element of that homotopy group is gone. That is exactly, well, when you construct more spectra or more spaces in Naolekar-MacLane space, that is actually what you do. There's some homotopy you want gone, so you put a cone on the elements you would like to kill, and categorically you would put it in an exact triangle and take the third term. And you do this until you get this thing called BP, pointy brackets N, whose homotopy groups are just this. So what you do is, well, for all the Vn plus 1 onwards, you basically put a mapping cone on, and then those elements in the homotopy groups, they will be gone. But now we still have to invert the Vn. And how do we invert something? So that is quite nice. So you take, you start with this thing. You take the map Vn, and it ends, well, there's a degree shift. It goes here. And you keep doing that. And you keep doing that forever. And then you apply the co-limit. And this thing, the homotopy groups of this thing, are now the homotopy groups of that with this thing inverted. Well, why is that? Well, if you take this thing and you apply Vn again, all that you do is take that entire sequence and shift it one to the right. So you get the same co-limit. because for the co-limit, it only matters how it continues. So if applying Vn doesn't change anything, it means that it is now an isomorphism. And whatever that is, you call En and say, tada, there it is. And Kn, you do very, very similarly. Ring a ding, let me finish the sentence. A bit like mastermind, isn't it? You also start with BP, you kill homotopy, and you end up with connected K theory, whose homotopy groups is just that. And then you do another co-limit construction like so, and you get the promised Kn. Okay, so these will be the main players of chromatic homotopy theory. We will localize with respect to those. And I mean, if you've never seen it before, it might look absolutely off-putting, but this one will behave like P localization. This one will behave like P completion. I also mentioned the word K theory, so it will also have something to do with K theory, which is manageable, and you can calculate things and see things, and they're nice. So hopefully, this is not the kind of cliffhanger which makes you think, well, on Friday you can just sleep long. Hopefully, I will manage to convince you that these things are actually nice and doable and not as abstract as they might have looked in the last 10 minutes. So thank you very much for your attention until now. Until next time.
Thank you. Any questions?
Is the W local model structure a stable one?
Is there what?
Is a stable model structure?
Are you asking if the E local stable homotopy category, if you get a stable model category in the localization process? Yeah. Absolutely. And that is, in fact, a very good thing to ask, because most of these general localization references that I mentioned, like Hirschhorn's book, they do not necessarily ask themselves that. But when you have a stable model category and you have just some very easy conditions to check to see if the resulting localization is again stable, and then a lot of these technical lemmas become easier. But yes, so all this is still in a stable model category context.
Okay, I was asking this because then the homotopy category would be triangulated, as you said last day, right? So the homotopy category of the local one, then
all still triangulated.
Like, so then, like, if it is smashing, then I can see it's exact functor, the localization, but in general, is it local?
It is.
I mean, it's exact functor.
Yeah, localizing is always exact.
So, I mean, any way to see it other than in cases when it is not smashing?
I think that I can think of several. Let me maybe come back to you, and I can think about the best way of putting it rather than just dumping all the thoughts on you at once, but I will answer that. Okay. Wait for the microphone, please.
Yeah, so what will be the Bousfield squares for En and Kn?
I'm afraid you have to wait until my later talks. They will come in all their glorious generalization.
Construction of En. What do you mean by applying Vn to the?
Okay, so Thank you for asking. So generally, if you're saying that, let's say Vn is in here, then of course, I agree that that doesn't make much sense what I wrote. But you can, of course, say you take BP, which is the same as BP smashed with a sphere, and then you can apply, well, Vn is now mapped from the sphere to BP. You can apply this onto this factor. That's a ring spectrum, so you can multiply. And then, so basically this is Vn, and by abuse of notation, this is Vn2. But it does really do exactly what you think. I mean, that's a ring, and this element is exactly the thing that induces multiplication with Vn on that ring. Which, whether you consider it in here or in here, that is exactly what it does.
Any further questions? If not, let's thank the speaker.